Ever since it came to light that Rolls-Royce was suffering durability issues on its flagship Trent 1000 engines, the press have had a field day. All too quick to drag this historic British brand through the mud, media voices have been surprisingly quiet on the mammoth effort that has gone into rectifying the problem. Let's take a look at just what it took for Rolls to solve its biggest crisis. The issues surrounding the Trent 1000 used on the Boeing 787 Dreamliner were substantially bad press for Rolls-Royce. For a company that has its beliefs rooted in high-quality products and incredible reliability, the focus on the one thing that went wrong for the business was a gut punch to this world-respected brand. Rolls-Royce didn't shy away from the crisis, maintaining transparency throughout about what went wrong and why. Speaking in mid-2019, the company's Chief Customer Officer of Civil Aerospace, Dominic Horwood, noted that Rolls was working intensely with its customers to support the recovery, calling the crisis unacceptable. Nevertheless, media reports continued to bash Rolls for the problems with the Trent engine. On occasions, the company was even called out on engine malfunctions when it wasn't even their own engine on board. The media circus continued on its merry dance, blissfully ignorant of the hard work being undertaken within the company to right this wrong. But much less attention was lavished on the company's significant effort to get the Trent 1000 back where it should be. From having 44 aircraft on ground, or AOG, at its peak, Rolls-Royce successfully drove that down to 0 AOG by the summer of 2020. In its most recent update, the company suggested that the costly engine issue is done and dusted. Let's take a closer look at what it had to fix. The Trent 1000 power plant is an incredibly powerful high-bypass turbofan engine. At takeoff, the force exerted on each individual fan blade is around 100 tons. This force is equivalent to hanging 9 London buses off of every single blade. This means the blades need to be strong, super strong, in fact. And indeed, they are just that. Engine blades are crafted by Rolls-Royce engineers using an ancient form of metalworking to create a single crystal structure that's incredibly strong, while still managing to be incredibly light. Casting has been around for millennia, but at the Rolls-Royce Advanced Blade Casting Facility, or ABCF, this traditional craft is elevated to levels akin to science fiction. Here, engineers set about rearranging the metal alloys at an atomic level to eliminate microscopic grain boundaries that could make the blades eventually fail. It's a fascinating process and one which prepares the blades to work in the ridiculously challenging environment at the heart of a jet engine. But Rolls-Royce was faced with some unexpected environmental conditions that affected the durability of these expertly crafted blades. Over certain airports, new environmental conditions brought about mainly due to increased levels of pollutants have accelerated the rate of sulfidation. This is a reaction when contaminants come into contact with high-temperature air, such as inside of a jet engine. This made the intermediate pressure or IP blades more susceptible to cracks, thereby reducing their potential lifespan. This change in environmental conditions was further compounded by a design flaw in the high-pressure or HP turbine blades. The nickel alloy used in the construction of HP blades has a melting point of around 1,455 degrees Celsius, but temperatures in the heart of a jet engine are far above this. To maintain the integrity of the metals in the blades, they are coated with a low-conductivity ceramic, and cool air is fed around the blades via tiny cooling holes. The cool air is actually around 600 degrees Celsius, and thus not that cool, really. However, it's still relatively cool enough to make a difference. Speaking with the website The Engineer in 2017, Rolls-Royce's Chief of Materials, Neil Glover, stated the following: "Air passes through the cooling channels and exits through a myriad of holes in the surface of the blade to create an envelope of cool air around the blade. So the metal is never above its melting point, even though the environment is." Rolls-Royce discovered that these cooling holes could have been better designed. Every single tiny hole has its own size, direction, and shape. As such, adjustments to these would prolong the life of the Trent 1000. The final issue to be dealt with was the intermediate pressure or IP compressor rotor resonance. When the Trent 1000 was designed, it had fewer fan blades than previous models that were capable of generating the same level of power. Doing so reduced weight, which is a good thing. However, what Rolls didn't know was that, under certain conditions, the rotation of these blades created a resonant frequency, like chiming a tuning fork on a surface. This frequency caused a wave of excitement further down the IP compressor line, which could eventually lead to the cracking observed on some rotor 1 and 2 compressor blades. In essence, it was a three-pronged problem and not an easy part swap fix. Rolls-Royce set out to fix all affected Trent 1000 engines in record time. Not all Trent engines required attention, but those that did required a rapid response from the British company. Rolls-Royce invested in new tools, equipment and people and expanded capacity at its MRO facilities in order to deal with the problem. The first problem tackled was the sulfidation on the IP turbine blade. To guard against potential corrosion, the company introduced a new blade design with an improved protective coating and a new base metal. Next, the HP turbine blade was entirely redesigned. The manufacturing process was improved so that the cooling holes functioned more effectively all around. The compressor blades suffering cracks from the resonance issue were also redesigned and installed in all engines. But it was not just the engine modifications that challenged Rolls-Royce's capabilities. In order to reach the milestone of 0 aircraft on ground, the company had to come up with innovative new ways to tackle this sort of problem, something that has elevated MRO for a better future. For example, the company trained airline engineers to undertake their own inspections of the Trent 1000 using LibreStream digital visualization technology. This has become even more important during COVID, where sending engineers around the world became near impossible. Rolls-Royce states that it's looking to widen the use of LibreStream in the future to allow more engineers to conduct on-site inspections, allowing airlines more flexibility over their maintenance requirements. With all the efforts, Rolls-Royce achieved its goal of no aircraft grounded with this issue in June 2020. Chris Collerton, Rolls-Royce President, Civil Aerospace, commented on the milestone saying, "Reaching 0 AOGs is an important milestone for us, and our focus will be sustained to help our customers return aircraft to regular service as they recover from the impact of COVID-19, and to complete the fitment of upgrades throughout the fleet. This will deliver the performance that we and our customers expect. I know that reaching this point has required incredible dedication and teamwork throughout our organization, and I want to thank everyone who has played a part in turning this situation around." The efforts of this company to resolve the situation have been nothing short of incredible. Even with the impact of COVID and the huge loss of revenue Rolls-Royce has suffered as a result of fewer wide-bodies flying, it stuck to its promise and fixed the problem for good. Now, isn't that something worth making some noise about? In addition to our daily YouTube videos, Simple Flying publishes over 150 articles and a podcast every week. If you're looking for the latest aviation news and insights, visit simpleflying.com. Thanks for watching, and don't forget to like and subscribe before you go.